So I've arrived at the conclusion that what we call quantum entanglement is not real. It's a fake concept. There is no such thing as quantum entanglement. And now I'm going to explain how I've come to this conclusion. So I'm going to give you two examples of quantum entanglement, but I'm going to tell you the story of the experiments, of what's happening in the experiments in a way that's a little bit different from what you've heard before. So first I'll start with the Stern-Burlack experiment. That's where silver ions, silver atoms, are passed through a detector one at a time. So what happens is these silver ions are passed through a magnet, and depending on how the magnet is oriented, it will either go in one direction or the other. Because these silver ions are actually like magnets themselves, they will actually be oriented by the magnet to face either towards one way or the other, either towards one metal plate or towards the other. The way it happens is exactly like how if you flip a coin, it'll either land face up or face down. And that's because the coin is flat, the table is flat. It may not be, the coin could be oriented in all sorts of other possible ways, but eventually it has to settle in one of these two ways. Exactly the same kind of thing is happening with the silver ions. So what you end up with is binary division of locations where the ion will eventually end up. Once you look at this experiment in this particular way, the concept of entanglement never enters the picture. The only reason the concept of entanglement enters the picture in this particular experiment is because physicists don't believe that that's what happens. They assume that the ions are traveling through an absolutely perfectly frictionless environment. And so there is no way for the electrons or the ions to become oriented in one direction or another. Instead, they will just process. But if you can imagine a so-called empty space containing some positive level of energy or some positive level of mass, why not imagine that there is at least some friction? Not absolutely zero, but just a little bit more than zero. That's all you need. And if you do that, you don't need quantum entanglement to explain what's happening. The second example would be with polarizing filters. To understand this, just imagine that you have waves of light passing through a polarizing filter, which breaks the light into its vertical and its horizontal components along some dimension, some arbitrary dimension, whatever. That's how the filter is. It has sort of a direction, a preferred direction, which it polarizes the light into. So the light naturally is in all polarities at once, or a range of different polarities, a mix of polarities. But what comes out of the filter is only one polarization direction. So what happens is the filter or the lens is breaking the light into horizontal and vertical. The vertical is allowed to pass through, the vertical component, and the horizontal component is absorbed. If you think about it that way, then it's very easy to explain how adding an additional filter in between can actually increase the amount of light that goes through. There's no mystery there. The only time you end up with a mystery and the need for the concept of quantum entanglement is when you imagine individual photons, little particles like billiard ball like things, traveling through the filters and either being absorbed or not absorbed, and having particular orientations on an individual level. I would say that model has to be incorrect. You have to look at it as waves passing through. And then that still leaves us with the challenge of explaining why you see little dots appear on a screen. Why does it look like we have little particles of light, little photons? Okay, that we still need to explain that, but we don't need the concept of quantum entanglement if we just think of it as waves going through lenses, and the lenses are taking the vertical component of the wave and absorbing the horizontal, so that what ends up passing through has a definite, consistent polarity. With that model, there's no need for time reversal or retrocausality or entanglement or any of these other concepts. So once again, all we have to do is, with respect to the silver ions, is just not assume an absolutely frictionless environment. And with respect to photons traveling through polarizing filters, all we have to do is assume that we're dealing with waves. If we do that, we don't even need the concept of quantum entanglement, which should make everything a lot easier to understand, because quantum entanglement is incredibly difficult to believe and to understand. So I'd say we're better off without it. And there's actually really no evidence of it.